Frank Sottile has taught Texas A&M since 2004 and was the founding chair of the SIAM activity group on algebraic geometry. And we're delighted to have Frank speak today about applications of Bernstein's other theorems. So Frank, take it away.
Yeah, well, thanks a lot for having me speak. Welcome to my home in Texas, where none of you will be next week, except for those who are already here. So today I'm going to discuss some uses of Bernstein's theorem in applications and some recent examples of non-generic systems that are nonetheless Bernstein-general, which I'll make clear. And I think this is somewhat like a methods talk. These are techniques that people are using in their work. So I'll just get started. So a monomial is, well, for me, I'm going to write it as x to the alpha, and this is x1 to the alpha 1 times xn to the alpha n. Here, x we'll think of as a non-zero complex, as in the n-dimensional torus, and alpha, of course, is a character of the torus, so that's how I identify this with z to the n. And then a polynomial. So this is a Laurent monomial because these can have negative exponent. These can be negative, and hence this has to be include the non-zero complex numbers. So a polynomial is just a linear combination of Laurent monomials, and we want to record what monomials can occur. So this would be complex, although sometimes this, of course, in applications, this will be real in some appropriate sense, oftentimes. And A is a finite set. A is Zn. I want it to be, it's finite since it's a linear combination, and it's called the support of F. And these don't need to all be non-zero, but I want to keep track of the possible monomials that can occur in my polynomial. And the reason that we identify this is, many people know Bernstein's theorem, and I'm going to state it in a moment, is that this set of monomials which can occur, or rather their convex hull, is a multivariate version of the degree of a polynomial. And this is understood best through Bernstein's theorem. And it says, okay, so I'm going to take a list of polynomials. These are polynomials with the support of Fi is some set Ai. And the first part of the theorem says that the number of isolated solutions in the complex torus to, well, the system F equals 0, which is really just F1 of x, the common zeros of these n polynomials. So the first part of Bernstein's theorem is a bound. Oh, sorry about the focus. The camera's smart, so I can't tell it to focus on the board. The number of isolated solutions is at most some number called the mixed volume, and I'm not going to define mixed volume. It's a number of the convex hull of each of these supports. And I'm just going to write MV for that, just for simplicity. And I'm not going to define what mixed volume is. The point is there's a number that one can determine, if you're lucky, or at least you know how to define it, which gives you an upper bound on the number of solutions to a set of isolated solutions to a set of polynomials, counted with multiplicity. And it says, and the next part is when the system of polynomials is general, in the sense that, meaning there's an open subset in the space of parameters of these polynomials, which are just vector spaces, for which the following holds. So when F is general, we have equality. And so this is often called the Bernstein bound, and you have to be careful because general in algebraic geometry means there's some open subset for which this occurs. And I want to point out that if all these supports are the same, or rather if their convex hulls are the same, I'll just say that the supports are the same. It doesn't really matter. Then the mixed volume is simply the usual well, it's the volume of any of these. But here I'm going to take what's called the normalized volume. For people in the know, that's where a standard simplex is volume 1. Okay, so it's n factorial times the Euclidean volume. I'll need this later on, and also the convex hull of AI is called the Newton is the Newton polytope of the ith polynomial. So these are some terms most people know of. So that's Bernstein's theorem. I want to talk about Bernstein's other theorem. And I'm separating them out because in part in his paper, he writes there are two theorems in his paper. Even though this is the Marquis theorem, the one about the bound and the equality, I want to argue that his other theorem is really the keystone of the whole story, and this is what we need to heed in applications. So let me make a couple definitions so that's apparent. So take a integer vector. This is really a co-character for those in the know. And then given my set A, I want AW to be, okay. Okay, I'll write this right. I'll say what this means. So this is so you look at the linear function given by the dot product of W on the set A. You look where it's minimum. You look at the minimum value, and you look at the elements of A where this is minimum. That's what argmin means. I was confused when I first saw this from reading a paper, but I later understood it. Okay, so this is the place where the minimum is attained. So if W is pointing in some direction and A is a collection of integer vectors, it would be the place where this linear function is minimum. It's the face exposed by W. And then if the support of F is A, then I'm going to write F sub W to be the sum over where now I'm restricting to the minimal to the part of the support where the linear function is minimum, and this is the part of the polynomial which is supported on that face or that face of the support of F, and then as we have our system from Bernstein's theorem, so a facial system, which I'll write FW. This is F1 W up to Fn W. Take the same, for W, take the facial polynomial, the part of the polynomial supported in the face, and this is the facial system. Now, one thing to notice, because W, the dot product of W takes the same value on all the exponents in here. This is really quasi-homogeneous, and it's actually in fewer variables than that secretly, because it's and so this is in less than n variables. Yes.
Could you, or Maggie, could you try to fix the settings so that people's see Frank's image larger?
Oh, well, mine appears larger on mine. You want to pin the video. So are people seeing a tiny little window? That's too bad.
Is that better? Cool, thank you.
Okay.
You're good, keep going.
Okay, okay, well, I don't know how good I am, but this is working okay. So then Bernstein's other theorem, it says that the number of solutions to my system is equal to the mixed volume. This is this equality here. It tells you exactly when this occurs. And it's very powerful. I mean, it identifies exactly the discriminal situation when you do not have equality. And it says if and only if for all non-zero weight vectors in z to the n, FW equals 0 is the empty set. So there's no solutions to these facial systems. And I want to point out this, I'm sorry, this is equivalence. And this is the key to his famous theorem. Because in proving his theorem, and he needs to use non-generic polynomials that are not general in this sense, and the properties of mixed volume to show that the mixed volume is the correct number. And I'm going to call, okay, such F is called Bernstein-general. So I mean, I could have said these were Bernstein-general, but here's an exact criterion for when it's Bernstein-general, which might be checkable. Although when you first start thinking about it, it's a little scary, in fact. At least it was to me. So there's some advantage of being Bernstein-general. The first one is you get a nifty formula. If a polynomial is Bernstein-general, you know that the mixed volume is the number of solutions. But that's advertising. But more importantly, there's a numerical method due to Schoenfels and Huber, and it's been implemented many times, which solves sparse polynomial systems. And in doing so, it follows mixed volume number of paths. And so when something is Bernstein-general, no path is wasted. It's very economical. We use the term optimal. So there's an optimal numerical algorithm for finding solutions to a Bernstein-general system. And so if a system is, if you know a system is typically Bernstein-general, you know that this homotopy is the best way to solve it, or at least one of the best ways to solve it. Okay. So, but now what I'm going to spend the rest of my time talking about, so this is, okay, are non-generic, but Bernstein-general systems in the real world. These have occurred in people's work in recently, and I think we should pay more attention to them. I was a little bit surprised when I noticed these occurring, because in my experience, coming from when I first did work in Schubert calculus, we have systems of polynomials that have they're complete intersections, but have far fewer solutions than predicted by Bernstein's theorem because of the nature of that. And there are methods to understand those called Newton-Kunkov bodies, which are even harder to deal with. But the fact that there are oftentimes non-generic systems and applications which are nevertheless Bernstein-general is something to pay attention to. And I'm going to talk about 4 recent papers, which maybe 5. It's hard to count, but recent work in which this has occurred. So the first one, and this will be interesting as you'll see at the end. This is due to Serkan, Isabel Shankar, and Angelica Torres. And what they're doing is, so I'm actually not going to, I'm going to, rather than give the background for these results, I'm going to mention some keywords, say what they did, and explain how it's Bernstein-general. So they studied what's called the central curve in interior point methods, which has been studied a lot. So interior point methods it's a way to solve optimization problems. You have a convex body, and you have an objective function, and starting from some point in that body, there's a well-defined path called the central curve, which I don't know if it starts at some point in the body, but a central curve which you trace to the optimal value in these methods. And there's a question about what's the complexity of that curve. It's total curvature. Another measure of complexity is the degree. So they studied the central curve. In particular, they studied its degree. And here's a theorem from their paper. It's theorem 3.3, the version that I got on the archive. It says for a general, and please read their paper what they mean by general linear program. In fact, these are, like any talk, this talk is an advertisement to read papers, so you should read their paper. For a general linear program, their paper talks about semi-definite programming, but I'm talking about this result, which is in linear programming. The degree of the central curve is, well, I'm not going to give a formula. It is, although the formula is easy, it's the volume of the Newton polytope of their formulation. So okay, so let me explain. The central curve, it's defined by some polynomials, and then the degree of it, you add a linear function, linear equation to that. And then in the formulation that they chose, the points are a complete intersection with essentially the same Newton polytope, which is actually a product of simplices. And they showed that the degree is the volume of the Newton polytope of their formulation. And the proof has two parts. The first part is by Bernstein. It's less than or equal to the volume, because Bernstein's theorem is a bound for the number of isolated solutions to a system of equations with a given Newton polytope. But what's nifty is they didn't have to do the hard work implied by Bernstein's other theorem. Is that work of Jesus, Sternfels, Parent, and Cynthia Vincent. They had shown that the degree is at most some number, which is in fact equal to the volume. So they'd already found a lower bound for the degree, which turns out to be the same number as the volume. And so upper bound equals lower bound, end of proof. So there's corollary here, is that their formulation of these authors is Bernstein-general. Now, you're not going to really care about computing the points on the degree of a general linear section of the central curve necessarily, but it's interesting that they're able to deduce its Bernstein-general without actually checking the facial systems. And well, their paper has three sections, one of which I did not talk about, and I'll talk about the third section now. Is there's in their theorem 4.1, it's they're looking at general quadratic programming, which is another optimization regime related for general quadratic programs. The degree of the central curve is less than or equal to the volume of the Newton polytope of a formulation that they give. So here, this is only an upper bound because they have a formulation which has it's related to this formulation, and so it's an upper bound by Bernstein's theorem. They do not know equality, and it's open. Is the formulation Bernstein-general? So I didn't argue for you that their polynomial formulation is not generic in that there are not enough parameters around to fill up the space. But that's the case, and here's the question: so this is open? Is it Bernstein-general? Now, one could, if you're strong enough, examine all the facial systems, or one could maybe find a lower bound in some other method. But I think maybe Serkan or Isabel or Angelica will tell us after the talk what's known about this right now. Okay. I'm going to go talk about it. I'm going to need to disappear for 10 seconds because I think I left 2 sheets of paper in my office. Oh, Jesus.
Okay, so while we have this little 10-second break, if people have questions or comments, feel free to put them in the Q&A, and we can have these ready when Frank makes the grand re-entrance.
Yeah, I'm back.
Welcome back, Frank.
Yeah, sorry about that. As I told you, there's a little bit of chaos. Well, I didn't say this before, but a little bit of chaos in getting set up. This is my kitchen, and my adult children who are staying with me were well aware that I had a talk to prepare for today, and they were still making their breakfast when I had to get online. So it was a little interesting. But at least there's one time at an AMS meeting, at JMM, I was giving a speed math talk, and I had a babysitter. I look after children at that meeting, so I brought them with me to the talk. And this is when we had acetate slides, and I turned my back to this projector to go look at the board, and my daughter and son stole my slides and ran out of the room. So, you know, this wasn't so bad. Okay, so here's another result. This is due to Lindbergh, Nicholson, Jose, and Wang. And I guess I had to put this in here because Jose invited me to speak. in fact, maybe that was a requirement. Anyways, I don't know. So let me explain this. So I want X to be, well, I'm going to use the variety notion, but it's the variety of some polynomials, K polynomials in C to the N, or maybe R to the N, or maybe R plus to the N. It's going to quickly become complexified, so it doesn't matter where I start out with. This is, let this be here, K is less than N, be a complete intersection. So this is a variety that's presented to us as its codimension is K, and it's a complete intersection. Maybe it's general, so it's smooth. Well, we'll say a little more about that. Now, they're looking at optimization, a general optimization. It affects a polynomial optimization on this variety. It's to minimize some objective function, which is a polynomial, on this affine variety. That's a very general nonlinear optimization problem, hard, typically. And we're going to look at two in particular today. So the first one is maximum likelihood. Hope I spelled this right. Likelihood. And here, things are real. In fact, maybe positive real, you'll see. And here G is, so U is just a point in R to the N, maybe positive. And you want to summarize some, well, actually U doesn't need to be non-negative, but you can see here, well, actually log of xi. So you're taking the coordinate-wise logarithm of the absolute value of x. I guess it could be complex even then. And then I'm taking the dot product with U. So that's the function you want to minimize. That's for maximum likelihood, or maybe there's a negative in there. I'm looking at critical points, so I don't care about signs. And the second one is Euclidean distance degree. So here G is the Euclidean distance from between U and a point on the variety. And well, you can square it because you can you're minimizing this number is the same thing as minimizing the square, which becomes algebraic. Okay, so and I'm not presenting all that's in their paper, just a couple of things that I can suggest. So then using KTT, Kurosh, no, it's a KKT. I can't remember. Did I get Jose? Is it KKT or KTT? It's KKT. Kurosh, Kuhn, and Tucker. Okay, or which is really just Lagrange multipliers like we teach it. It's essentially Lagrange multipliers like we teach it in advanced calculus or in Calc 3. You know, if your students are strong enough, that what you do is so the idea, we want to maximize these functions or minimize them. And what we do is we search for critical points, and you can think of it as an algorithm to solve the problem. You find the critical points and then you check which one minimizes it. Or you could check that the number of critical points is a measure of the algebraic degree, or rather complexity, of these optimization problems. Either way, we're going to search for critical points, and that's why I can put a log in an algebraic geometry chalk, because when I take the derivative, it's going to become an algebraic function. So you get what I'm going to call critical point equations. And the first one, well, okay, for solving this problem, you get your polynomials that have to vanish, together with you take the various partial derivatives of this, and you get ui minus xi. This is really a vector equation times the, I hope I get this right, j from 1 to k. There's Lagrange multipliers, and then the ith derivative of fj. So you're basically saying that this is a linear combination multiplied by xi of, if you look at ui divided by xi, this is really a linear combination of the differentials. You're saying that vector, well, that it is what it is. The second one for Euclidean distance degree is a little bit easier. It's the same. First, you need to be on the variety, and then you have equations of the form ui minus xi minus, so here's the vector, minus the sum over j lambda j di of fj. Again, this vector from your fixed point to a point on the variety is parallel to some, it lies in the span of the differentials. Okay, and now here I can let things be complex, so u and x are complex, and the number of solutions is the blank degree of the problem. So maximum likelihood degree, Euclidean distance degree. And okay, so their theorem is that for F1, Fk general, given their support, both of these systems are Bernstein-general. Meaning that the mixed volume of this collection of polynomials is the corresponding degree. And you'll notice that your freedom is only really in the choice of u, and in the coefficients of the fi, which reappear here in these Lagrange equations, which there's n of them. And so these are not general in the sense of being an open subset of the space of sparse polynomials. Nevertheless, they're Bernstein-general. And the proof, which initially it seems scary, you basically analyze all facial systems. And when I read their paper, I was surprised that it was so tractable. Because the case when k is 1 was I did earlier with Paul Breiting, just of the Euclidean distance degree with Breiting and Woodcock, and it was tractable there. But I was just thinking about the case when k gets larger made my head spin. And the first picture is an example of this. So the first picture, which you should have on your computer, if you're not looking at me, is a biquadratic curve in the plane, a point U in the center of an oval, and then it's showing the 12 critical points. And 12 is the mixed volume in this case. In fact, Woodcock came up with a very nice formula for the Euclidean distance degree of a hypersurface whose Newton polytope is a box. And so 12 is the first case. Okay, I guess Jose just put the picture up. Okay, let's see. All right, so now let me talk about the last topic, which is maybe least developed. And this is comes from work that I did with Ngoc-Tran Do, Peter Kushmat. These are mathematical physicists in my department, and then also with Matt Faust, who's here. He's a graduate student, and I'm going to talk about just part of all of this. So our object is a periodic graph That's what we're going to start talking about. Gamma is a simple graph with a co-compact Zn action. I say a free Zn action. So so my next picture is an example of that, and I'm going to talk about that picture in a moment if I can get it up on my computer. So what you see there, it looks like a cross. I'm showing you. Okay, you imagine the plane is tiled by copies of the yellow region, which is a fundamental domain. There are two vertices of the graph in the fundamental domain, and essentially it's connected to those two vertices are connected every possible way to the vertices to the left, to the right, to the left, up and down, and then this tiles the plane. This is an example of a dense graph where I specified which directions I can leave the fundamental domain from, namely plus or minus x, or plus or minus z1, plus or minus z2, and then I've drawn all possible edges given those data. That's a dense graph. That's an example of a two-dimensional periodic graph. In that case, n is 2. Co-compact means there's finally many orbits, and simple means there's no loops. And then, well, what you do is, given this, you use a function from the edges of gamma to, well, R or C that's Zn invariant. This is a labeling, and so it's constant on every orbit. And I should say a little bit, the mathematical physicist, this is a generalization of it's a mathematical model of a crystal of some regular structure, and these edges are interactions and the weights are interactions. And then there's the Laplace. So the Laplacian is when this number this is all 1, and that's typically highly degenerate. Beltrami equation. So I want f to be a square summable function on the vertices of gamma, and then well, L of f at a vertex. So the operator is just a simple difference operator. You look at all pairs of edges that are incident on V. You take the corresponding weight, and then it's f of V minus f of u, and depending on who you talk to, it's f of u minus f of V, but it doesn't really matter. And so you have this operator on this Hilbert space. It turns out that, I mean, not so hard, that when these weights are real, this is self-adjoint. And that's interesting for algebraic geometry purposes in a moment. But there are many questions about its spectrum as a self-adjoint operator when the weights are real. And I'm going to sketch one of those questions, not even the full part of the question, but it's an approach to this question. So, but before I get to what that question is, or what it is, I need to do a little bit of math. I'm going to do a Fourier transform. So first of all, you want to choose, or I've chosen, a fundamental domain of this free action. It's just some subset of the vertices of the graph, and now people, just like I drew in this picture, people typically draw these think of these as occupying physical space in Rn, and it'd be a fundamental domain like in a crystal action. Then after Fourier, which takes f to its well, okay, so f in this Hilbert space goes to f hat in another Hilbert space, and this other Hilbert space is well, you take square integrable functions on the torus. It could be on the compact torus inside of here as well. That's okay. But then you take function. Well, in fact, you associate. So this is a vector whose components are indexed by v, and each component is an integrable function, a square integrable function on this torus, or on the compact torus inside of there if you're a physicist. This is not dual. Okay, and then the operator for v in the fundamental domain is simply this. So if I apply this to f hat, I look at v. It looks very similar. It has the summation is a little bit longer. So I take well, I want u plus alpha comma v to be an edge of the graph. Here, u is in the fundamental domain because I want to express it there, and alpha is the action. So if there's an edge within the fundamental domain, alpha is 0. If it leaves the fundamental domain, like you see in my picture, alpha is whatever that translation is, which is naturally an exponent vector. And then you have c u plus alpha v, and then it's usual before it's f hat of v, but now it's minus x to the alpha f hat of u. So it's and you know, this is what happens is when you do Fourier transform, this the reason we're able to identify the Fourier transform of this as this finite dimensional space is because there's an action of characters on this as you translate. It's really sections of a line bundle if you want to think about it. And what's interesting is L is a V by V matrix of polynomials. So this is really an object of algebraic geometry. I mean, this is not recently observed. Giesecker wrote in a short but important book proving part of the conjectures here for certain graphs when n is 2 using the classification of curves. But okay, so what I'm interested in is something called the dispersion relation. Actually, there are many words for all of these in mathematical physics. I think everything has 3 or 4 words associated to it. And the dispersion relation, I want to explain to you. So I'm going to define psi to be the determinant of lambda times the identity matrix minus the matrix for L. So this is really just the characteristic equation, characteristic polynomial for L. But since L is of Laurent polynomials, this is okay. You know, this is an element of C adjoin lambda and say X. It's Laurent polynomials and lambda. And then the dispersion relation, I'm just going to write D for because I don't really need this notation. It's simply the variety of this characteristic equation. And this is contained in C star to the n cross C lambda. And now you can look at my third picture. So when my weights are real, this is really well. So when the weights are real, the fact that L is self-adjoint means that I can look at this in the real torus, the compact torus across the real line there. There's a twisted real structure that has to do with this. This is in which there'll be a real algebraic variety, and that's the picture you see there. The base is really the 2 torus just spread out, and then you see there are 2 sheets above there because it's a 2 by 2 matrix, so there's 2 eigenvalues. And the point is that the spectrum of L is the projection to C lambda, or in that case R lambda of D. And the spectrum is the 2 bands you see that are thickened on the left in that picture. And the conjecture from physics, this is the old physics conjecture, and in fact, it's not a conjecture in physics. It's just something they just assume. It's always true, obviously. Is that and much more generally than this, it's always assumed, is that the real critical points of this projection are non-degenerate, and some other things about isolated and whatnot. And you see this in this picture here. Each of those sheets, it projects onto a interval and the x-axis. In fact, that's a perfect Morse function. Each of the sheets has a maximum, a minimum, and 2 saddle points. So this is implied by saying that this function lambda is a Morse function. So that's another approach of this. But and this conjecture is needed for I guess, well, it's needed many times. I mean, if you're near the edge of a spectrum, it means that your particle that you're modeling by your wave function, which is really what's going on here, has mass that you can understand. It it looks like a well. Anyways, so let's look at the critical point equations here. So they have the form, this determinant, and then xi dc dxi. So since xi is never 0, I can always multiply by xi. And the nice thing about this is that the Newton polytope of these differentials, of these, okay, first of all, because of the nature of these graphs, this Newton polytope is kind of central. There's an isomorphism, x goes to x inverse, which preserves it. And it turns out these are the same Newton polytope. And these have Newton polytope, the Newton polytope of psi, which is well, I mean, it depends upon the graph exactly what it is. And the theorem that I wanted to mention, so this was observed in a special case in a paper with Cushman and Doe, and more generally with Faust, is that when gamma is dense, in the sense that I sketched before, but we don't know about this more generally. Dense means that you have vertices in a fundamental domain, and all the edges are there, so all the interactions are there. And together with whenever you leave the fundamental domain, if an edge leaves the fundamental domain, so do all possible edges into these other parts of the graph. Then the result is the critical point equations are Bernstein-general. Actually, it's a slight lie, because well, this is a variety which has a projective embedding, and it has a boundary. Notice that this is not the non-zero points of lambda, so that boundary is a little less than the boundary of the toric variety. There are no solutions in the toric variety, because there's always solutions when lambda is 0 in this case. But I think it's good enough for government work, and I'm a government employee, so that's the end of my talk. So this is another realm in which in fact, for me, this is the first place that I ran into this example. Once you know something about their finely made critical points and have a bound on them, it allows us in any particular case to prove this this conjecture. It would be nice, and this is certainly what we're looking for, is to try to understand this more generally not on some case-by-case basis. And there are actually many questions open about the dispersion relation for a discrete operator and discrete periodic graph. And I think I'm over time, in fact. Sorry, Jose, I'm sorry.
Oh, fantastic, Frank. Well, thank you very much for the wonderful talk, and you're right on time.
Well, you told me 45 minutes plus questions, and I didn't allow questions, so sorry.
You're fine. So yeah, if people have questions, put them in the Q&A. Otherwise, we'll jump straight into informal discussion, but I have a question. Sure. So do you think with these methods here that you discussed, that you can find a case where the conjecture that the physicists believe is false, or disprove it in some example?
So it actually is false for some graphs. I mean, for instance, so it depends on how you make this conjecture. And also it's a little more complicated. So if you take graphene, which this is what a periodic domain, you take you tile the plane by hexagons, and you just have very minimal connections, and this is your fundamental domain. It turns out that there are 12 critical points, but 2 of them occur with multiplicity 2. But however, when they're complex, you don't see them in the real picture, and the real picture looks beautiful, like the ones I showed. In fact, it looks exactly like the one I showed. But if they become real, they connect the 2 sheets together, and you don't care about it. You only care about the edges of the spectrum. So there are many ways to view this conjecture. You can say a Morse function over the complex numbers. You can say a Morse function over the reals. Then it becomes a sort of semi-algebraic question. There's the fact that the real critical points, the degenerate critical points, when they become real, connect the two sheets together. That's also related to other questions about the connectivity of the spectrum, and real algebraic geometry suggests that you should expect these to occur in the interior of the spectrum and not the edges of the spectrum. So singularity theory may come into play there. And as for the real algebraic geometry, this is the real variety here, like the one you're looking at on your page, is an example of a hypersurface, of a real hypersurface in a toric variety with a non-standard real structure. Just like the sphere is a toric variety, it's the real points of a toric variety, the quadratic with a non-standard real structure.
All right, thanks, Frank.
I mean, in fact, I have some undergraduates that are working to understand. So we have this theorem for dense graphs. And if you start deleting edges, if you play Jenga on it, for instance, for those people who know what that is, eventually you're going to get to, there's a poset, and eventually you're going to get to graphs where the Newton polytope changes. They're no longer Bernstein-general, where there are singularities, or where there's even a factorization, which is another like a simple question is this polynomial irreducible? Yes, it is actually. And also, is the variety irreducible? That's a question people ask, and so we have some students looking through this to try to generate some conjectures. It was a good way to keep people occupied during the pandemic.
All right, great. Okay, so I don't see any questions in the Q&A, so then we'll toss it over to the informal discussion in a second. But let me just thank you again for a great talk. Okay, so now I'll pause the recording and then I'll promote people that raised their hand into panelists. I can try to do this.